In this chapter, we will discuss relational model concepts, how a relation impacts a schema, how a relation looks visually, characteristics of relations, the types of constraints associated with relations, how a relationship database schema looks, types of states, integrity, update operations, and potential violations related to update operations. A relationship connects two or more items together, as you probably know. An overview of the topics I referenced earlier. Formal model is how our brain leads us to believe the relational model should look. Practical model or standard model is how these connections are run within database programs or commands such as SQL. As you have seen throughout your coursework in mathematics and computer science, you notice they are intertwined, with computer science often relying on many mathematical concepts, arrays and matrices being examples. A relation sort of looks like a table you may see in Microsoft Access, with rows or tuples and columns or attributes of data. Here is a visual representation of a relation named student. We have multiple tuples with our attribute information. Notice the null values. If this information was provided by the individual students, that means they did not provide this data, or potentially based on data type was not supplied correctly. You might ask why the Social Security number is key and not the name attribute. Think of it from the standpoint where everyone has a different Social Security number, or from the Microsoft Access standpoint, where the primary key is often an auto number created for each record. Think back to the recently seen student relation. We would have student as our schema. We would have name, social security number, home, phone, address, office phone, age, and GPA. Think of the domain as a data type. In Microsoft Access, you see tuples as records. We can have multiple records in a table or query in Access, hence why our relation looks similar to a table in Access. However, formally, our tuples are ordered inside brackets based on our attributes. This is not done in practice, however. Keep in mind, your attribute can change your domain/data type. International calling requires you to add a 1 in front of all numbers. Similarly, prior to 2000, date was shown as month, date, year, instead of the current usage, month, date, year. As you played around with in Project 1, the data type of your attribute can be defined or assigned in different ways to meet your needs. Just like an attribute can have a data type the same as another attribute, multiple attributes can have the same domain. The relation state can also be broken down into the relational database state and populated database state, as we will see later in this chapter. In this example, a longer customer name, over 25 characters, varchar 25, will not be possible. Notice again the connection between domain and data type. We have previously defined our schema of the relationship student in slide 9 as student with name inside, SSN, home phone, address, office phone, age, and GPA. In the example R, A1, A2, as seen, can you determine how many tuples and attributes we have? Let the bottom example here be your guide. We see 3 tuples with 2 attributes each. Here are the definitions in a more concise manner than previously seen. We will touch more on the populated state of a database later on in this chapter. Here is our student relation again. Can you write this relation out like we did in slides 13 and 14? Unlike a Microsoft Access table where we set the order of our fields or attributes, a relation is not considered to be in order. Remember how the Social Security number was key, but second in order? In Access, our key is almost always first. Notice how Benjamin went from first to last in our tuples. This is because there is no set order with relations. We can change this with commands, though. The more tuples, the more possibilities for the possible order. As an example, you cannot put letters into a phone number attribute if the domain is set up to only take number, dash, number, dash, number. As we previously saw, a null value is possible. Component values are simply the values which create your tuple. Each component builds the tuple. Each piece of data helps in building your relation table. Here are the 3 most common constraints related to a database with an example. You will notice no example for application-based or semantic constraints, as these may not be clearly seen and can be hard to interpret. These are the primary constraints for a relation key: entity integrity and referential integrity, which will be covered in depth in this chapter. Other constraints will be briefly touched on later in this chapter. A key can be the superkey of a relation depending on the information you need, but a superkey does not drop down to a key, i.e., lessen its importance, at any point unless you change this. Notice in this example, serial number is a superkey because it is unlikely to be duplicated, similar to primary key in Access. Make is a superkey because you can create a relation based on it, such as all Dodge Caravans. We have seen primary keys underlined in our previously covered entity relationship diagrams. Serial number here is made primary key and is very, very unlikely to repeat. Make, model, and year all can possibly repeat. Here, license number and engine serial number are set as candidate keys, with only license number set as primary key. Realistically, either or could be primary key, but as recently seen, primary key can be set arbitrarily. Notice how there are multiple Oldsmobile makes. We have seen this previously in visual fashion, but here is an explanation in words. We are simply stating a database is made up of tables or relations. Here we have our company database with our employee relation, department relation, etc. This should look very familiar based on our prior discussion on mapping. The relational database state simply means how does the database look now in its current state. This state can change every time you make a change to your database. A populated database state is where all information or data within every relation table of the database is inputted and available. Here is a visual of a populated database state. Notice all of our data is available to access. Primary keys cannot have null values, meaning the most important attribute in your entity must have values. If you intend to reference an attribute, the attribute you are referencing must have a value. Here is how we link together attributes using references. Ideally, we don't want to reference a null value because it provides us with no information. It is much easier to define our constraints for a relation now that we have learned how to map based on entity relation diagrams. You will notice the references are defined using arrows. Notice how most of the references are coming from the employee relation and others are coming from the department relation. See, most of our relations are department and employee. Here are some other types of possible constraints for your consideration. Here are the ways we can update a database relation by inserting, deleting, or otherwise modifying a tuple. We do this to our attributes in different ways. There are a number of ways to address the possibility of integrity constraints previously referenced. Here, we describe the possible violations associated with using the insert command. Here, we describe the possible violations associated with using the delete command. Here, we describe the possible violations associated with modifying a tuple or database using the update command. Hopefully, you now have an understanding of these concepts. Go ahead and try out this exercise on your own. See what you can come up with.